Alright, we're going to try this with a little bit of color here. First one's going to be multiplying and adding polynomials. It's also going to be simplifying rational expressions. But the main thing to remember is that x plus x is different than x times x. X plus x, when we combine like terms, is going to give you 2x, and x times x is going to be x squared. So if we look at the first problem here, there we go. When we're adding the two, we want to make sure that we don't get crazy with any sort of cross-simplifying that is only with multiplication. And so for this case, if we're adding, the main thing to remember when we're adding any fraction is to make sure that we have common denominators. So if we look at this, we have these two parts of it are common, but we need to multiply to make sure that we have common. So on this side, on the left side I should say, I need to multiply by x minus 2 so that the denominator is the same. Whatever I do to the bottom, I do to the top. And then on the right side, in order to have common denominators, I need to multiply everything by x plus 3. And x plus 3 on the top. And when we finish, I get this. When I FOIL all of these, that's going to give me my answers. And then when I want to combine this, now that I have common denominators, I can just go ahead and combine like terms on the top. I can do that specifically because this is a plus. If this was a minus, then I would need to treat this whole thing as one quantity, and if it was minus, I would have to distribute that minus to everything on the top. I think honestly that's the biggest thing people forget, is that this is minus the whole quantity or plus the whole quantity. However, since it's not minus, I can go ahead and combine. But again, if that was a subtraction sign, you want to just make sure to distribute that to subtraction and then go ahead and combine like terms. So finished, it looks like this. And if you wanted to, you could distribute at the bottom or FOIL everything. If that was asked, by all means do it. If not, then I would leave it like this in simplest form. As we move on to multiplication, things get a lot easier actually. We can go ahead and simplify as you would love to. And so if you notice anything on the top and the bottom, if you're going to multiply and then divide, they kind of cancel each other out. So as I look at this, I recognize these are x minus 2 on the top, x minus 2 on the bottom, so they're going to go ahead and cancel out. Same thing with x plus 3 on top and bottom, they're going to cancel out. So when I go ahead and cross off as much as I can, cross simplify, I'm going to be left with x plus 4, x plus 1, and on the bottom I get x minus 5, so I can go ahead and call that squared. And again, if you'd like to simplify this or expand this out, you certainly can, which would look like this. It's up to you, or really I guess it's up to your teacher whether they like it and they accept it in the first form or if they make you expand it out. Either way, they equal the same thing, and this is what you would get. If we look at this one, we see division, and I know that wasn't on the title at the beginning, but you might find division. It really isn't too difficult as long as you see division. You know that division is the same as multiplying by the reciprocal, so I can just rewrite this as multiplying, and then I would need to switch the numerator and denominator of the second fraction. And so I can go ahead and move these around, and now I have a multiplication. So if you want, go ahead and try this one, and then go ahead and pause it, and then I'll just give it a second and post the answer. It's also worthwhile to note that this can be simplified, or at least I call it simplified. We can rewrite these all in factored form, and so this will be good practice of that as well. So how do we write each one of these in factored form? We can do so multiplied by. So at this point, go ahead and pause it. We'll factor everything, and then if you can, we'll simplify. So in factored form it looks like this. We've got an x plus 5 over an x plus 5, an x plus 4 over an x plus 4. We can cross simplify x minus 3 over x minus 3, and x minus 9 over x minus 9. So at first you might not see this at the beginning, but once you factored everything, it really does make it quite simple. And then your answer is going to be, this whole thing equals 1, but the answer is 1. However, depending on if you have to give these or not, you also know that x cannot be 9, because if it was 9 here, this would equal 0, and you can't have 0 in the denominator. It also can't be a negative 5, because that would be a 0 in the denominator. And then same thing on the right fraction, you can't have a negative 4, because that would be a 0, and you can't have a 3. So as long as x is not these, no matter what you put in for x, the answer is going to be 1. So depending on, again, what you're asked for, you may need to include all this, but there's everything for you. Alright, so your second one's going to be differences of squares and differences in sums of cubes. So for this first one, we notice that we've got no x term. There's a reason for that. If we are going to factor these, if we notice that this is a perfect square, we can always try this. And so x times x gives me x squared, and then 7 times 7 gives me 49. And then if it's a difference of a perfect square, we can go ahead and subtract and add with these opposite operations. We can go ahead and prove this when we FOIL. We've got x squared. We've got then x plus 7 and x minus 7. Or sorry, we got plus 7x and minus 7x. Those are going to cancel each other out, and that's why there's no x term in our original. And then finally, with that 7 times 7, we get 49. Since this is a subtraction symbol, that's a negative, and that's where that minus comes from. You won't be able to have a perfect square like this with an addition symbol. It really only comes with subtraction, and that's because at the end, we have that negative and positive cancel each other out for that x term, and so that negative is always going to give me a minus the square at the end. And so something to look for. If you end up having a coefficient with x, again, as long as it's a perfect square, not a problem. If we look at the right side here, this is a perfect square, so 3 times 3 is 9, x times x is x squared, 6 times 6 is 36, and we know it has to be plus and minus. It doesn't necessarily matter which one is which, as long as there's one of each, because again, that's going to be plus a term minus the same term. They cancel each other out, and then you're left with, at the end, a negative because you have one negative. If you were to try to take this a step further and actually solve for x, then over here, x would be 7, because if this whole thing equals 0, then any one of these terms can equal 0. And so if the left term over here equals 0, then x has to be 7. Over here, if this is going to equal 0, then x has to be negative 7. And then we can set the same thing over here. If 3x plus 6 equals 0, or 3x minus 6 equals 0, we can then solve for x and go ahead and write our answers. After you get your answers, I would always recommend double checking them as well, as long as you have your calculator. For the first one, just type in 7 for x, test it out, make sure that 7 times 7 minus 49 does in fact equal 0. Same with any equation. When it comes to sums and differences of cubes, the formula is really your best friend here, and so as long as you have access to this, great. If not, memorizing it does help, but it's the same principles in a way, but you're looking for cubes. So here, I've got x to the 3rd power is a perfect cube, 8 is a perfect cube, so I am able to use this, and so I'm going to write my terms here. X cubed is x cubed, 2 cubed is 8, and so I can then go ahead and square my first term, square my last term, and then for the middle, just multiply these terms. Oops. 2x. And then it really just comes down to knowing where to place our addition and subtraction. if this is subtraction, then I go ahead and put my minus here, and the rest are pluses. You are always going to have one minus, and if it's in your original, it's the first one. If it's not, it's the second one. The last term is always going to be positive, so you're always going to have a plus. At this point, I would recommend pausing and just trying the first one on your own. So I'll give you a second to do that now. And then I am going to do what I did with the first one. If I look at these, even with a coefficient, I'm looking for, is it a perfect cube? And so if it is, 3 times 3 is 9, 9 times 3 is 27. So this first one is a 3. And again, don't forget your x. And then 1, surprisingly enough, is a perfect cube because 1 times 1 times 1 is 1. So 1 is the perfect square, cube, anything really. So that once I have my two terms, I can then again square the first term. 3 times 3 is 9. X times x is x squared. Square my last term. 1 times 1 is 1. And then in the middle, 3x times 1 is going to give me 3x in the middle. So again, I look for what this is. If this is plus, this is going to be plus. My last term is always plus, so then there's my minus. For the second one, if I look at this, I actually see -2 is not a perfect cube, 250 is not a perfect cube, so that gives me cause for concern right there, my first pause. However, if I'm asked to do this in the perfect cube section, there's probably a way to do that. Never forget, if you can factor out a common term. And if I factor out this -2x from my first one, and I factor out a -2, actually that would make that a negative then. This would be 125. If I do this and I look at this term, or what I have in the parentheses, then I actually do have a perfect cube. I have x cubed, I have 5 cubed. I just can't forget about this term here. It just ends up being multiplied by the whole thing on the outside. So I factor that out, it stays there, but I am able to then use my subtraction of cubes with this term inside the parentheses. So again, I then square my x, square my 5, and then in the middle, 5 times x, multiply these two together, and then go ahead and distribute my subtraction and addition again. Since this is subtraction, this is subtraction. It doesn't necessarily matter what you started with here, because this is what I'm actually using to write my sum or difference of a cube. So I want to just focus on what I'm actually taking apart. So again, at the beginning, once I can factor that -2 out, I'm really kind of treating it like a separate problem. Just don't forget to include this on the side. On a test or quiz, what this boils down to is recognizing what is or isn't a cube, and then making sure that you know where, again, a squared term is, multiply them in the center, and just know the pattern of where the addition and subtraction goes. And again, that first page really kind of has it out. You know that if it's originally up here a plus, then this is going to be, your first one's going to be a plus. You always know your last one's a plus, and so the subtraction is going to either be the first one or the second one, but there's only one. Good luck. So long division like this is actually kind of fun. I know that sounds crazy, but it's kind of like what you normally do for long division. When you have any two numbers, you, depending on the place values, you go ahead and line up your place value, especially if there's decimals. You want to then find out what the multiplier is, write it on top, multiply it to the term on the left outside of the division symbol, and then write your answer to that inside the division symbol, and then subtract. So we're doing the same thing, only now we're actually doing it with multiple terms. But the idea is still the same. So we kind of want to line up first our what I guess you would call a place value for this. And so since my term over here, my numerator, is 2x minus 3. I know it's got an x to the first power, and I know my first term inside has x to the fourth power, so I need to multiply by an x to the third power to be able to get a term that is x to the fourth power. So if I know the first thing I have to multiply by is x to the third power, then I need to line up my first number right here over my 9x to the third power. So I need to line up my terms, and again, I know that I need to get to x to the fourth. I have an x, so I need an x to the third. So that's how I know where I'm starting. So here I'm just going to go ahead and multiply by x to the third, because I know x to the third times, and I'm going to almost like distribute it here. X to the third times 2x is 2x to the fourth, and x to the third times 3 is going to be 3x to the third. Oops. And then if I subtract, I can go ahead and, oops, I meant to erase. I can go ahead and remove this because it doesn't actually exist, but that was what I did in my head. And I can then go ahead and subtract this term. Now, I just need to remember, and again, like everything that I subtract when it comes to polynomials or when it comes to these expressions, I'm actually subtracting the whole term. So what that means is this is a negative, and then I distribute that over here. This becomes a positive, so I'm subtracting the whole term. I distribute that subtraction, and what I'm left with is these cancel off, give me 0. Negative 9x to the third plus 3x to the third gives me a negative 6x to the third remainder. Now, I can't really just work with this, so I need to bring this next term down, just like I do with regular division. 21x squared, and then I can continue to work from here. So I'm looking to see what can I multiply by 2x to give me this negative 6x to the third, and so I need to multiply by a 3x squared, but I need it to be a negative, so that negative 3x squared times 2x gives me negative 6x cubed, and negative 3x squared times, if I distribute that negative 3, I end up with a positive 9x squared. When I subtract this whole thing, I'm actually subtracting again while distributing. So this is going to become a plus, this is going to become a minus once I've distributed that, and then I can go ahead and combine these, and I end up with, again, canceling these out, that's the whole point, and I end up with a 12x squared down here. And I'm going to continue doing the pattern. I can't do anything with this 12x squared. I bring this down. Unfortunately, I'm not really lined up. That's okay. You'll probably do a better job with a pencil. And then if I'm trying to get, again, I have 2x is my term. I want to get 12x squared. So what do I have to multiply by? I have to multiply by a 6x. So I add a positive 6x. 6x times 2x is 12x squared. 6x times 3x is 18x. And I'm subtracting it. And then at the end, I distribute my subtraction. And I end up with, canceling this off, a negative 8x, where I can finally bring down my 12. And then I have to try to find out what times 2x equals negative 8x. At this point, hopefully, I'm lined up and I have my last term is going to be a constant. So that ends up being 4. 4 times 2x is 8x. This 4 has to be minus then, so that I match that. So a negative 4 times 2x equals negative 8x. Negative 4 times negative 3 equals positive 12. And again, if I were to subtract this whole thing, I distribute. That means these are going to cancel out, and I end up with 0, so I have no remainder. So then my answer is right here along the top. So 2x to the fourth minus 9x to the third plus 21x squared minus 26x plus 12 divided by 2x minus 3 ends up being x to the third minus 3x squared plus 6x minus 4. Now if you end up with a remainder at the end, so not all of them end up perfectly subtracting to be 0. Let's say you ended up with plus or minus, I don't know, 10, 12. It's going to be a constant. So really it just comes down to your last term here. We're not going to do anything with decimals, so we're going to consider it like a remainder as a fraction. Let's say you had, 4 left over. What I would do is I would write my remainder then over 2x minus 3. So if it was a positive 4, I would add that. If it was a negative 4, I would subtract that. But then I end up having this fraction of my original term left. So I could just bring that up and write it as 4 over 2x minus 3, because that's what I'm actually taking this out of. If you don't have a remainder, life is perfect. If you do, that's okay. You can just make it into a fraction. No matter what, this fraction is going to be a lot nicer than what you started with. So that's how you would do long division. You're looking for lining up terms. You're looking for what is the term, the biggest term you have, and what do you multiply your first term here to equal your biggest term, and then don't forget to distribute that negative when you subtract. And so if I know I need a negative 6x to the third, like we do right here, then I need a negative 3x or a minus 3x squared as my second term, because I need to get that negative to match. Then afterwards, when I subtract, I can go ahead and distribute and cancel things off. So keep those in mind as you work, and I would find some practice ones, maybe just do 1 or 2 more, or redo 1 or 2 of those, because these won't be memorized. So look back in your book and just find 1 or 2 that you can practice. And gray brings us to simplifying radicals. So when we look at these, you want to see what power you're simplifying your radical to, or what power the radical's to. In the right side, you specifically see this 3, or on the left side, you don't have one. When you don't have one, you can always assume that it's square rooting. And so you're taking the square root. What I like to do is, again, find my prime factorization trees, however you do that. And so if I were to break this down, and I know that this is square rooting, I'm looking for my prime factorization of all my terms. In this case, it's only 12. When I prime factor it, I see that I have 2 times 2 times 3, and since this is to the second power, every one of these that I bring out, or every 2 that I have, I bring 1 out. And so here, what's left over is 3, so that stays under the radical. Big numbers like 108, depending on if you do divide by 2, divide by 4, whatever you want to do, break this down into prime factorization. And again, since this is a cube root, then I'm looking for 3 of something. So once I have 3, I can bring it to the outside here. And I have 2 times 2. I'm not going to leave it as 2 times 2 since I can't bring it out. 2 times 2 is 4. I'll just leave it as 4. But here I can take out the 3 because I have 3 times 3 times 3 embedded within this 108. And then I'm left with 2 times 2. And I want to make sure I keep this cube root here. So when there's just numbers, however, you're going to see bigger numbers than cube root, and you're probably going to see variables inside. So what do we do with this? We still want to prime factor everything, but we want to do each individual part of this. So I'm going to pause it here for a second and then write that out. So here's my prime factorization. 162 broken down is 3 times 3 times 3 times 3 times 2, and I'm looking for, again, my fourth root here. So I'm looking for 4 of something. So if I see 4 3s, I can go ahead and pull that 3 out, and I still have a 2 left over. If I see 4 A's, I can go ahead and pull that A out, and I have nothing left over. If I can cross off these 4 B's, I'm going to pull a B out, and I still have a B left over. And then for C's, I don't have enough to pull them out. So if there's not 4, I can't do anything with it. I need 4. So then these all have to stay inside. So what I have in black here, I pulled out, I have a 3, an A, and a B, and then I'm going to make sure I remember this is fourth root. What I have circled is what's left in there. So I have a 2, a B, and then I have C to the third power because I wasn't able to take any out, and there's nothing you can do to kind of simplify even half of that. It's an all or nothing kind of thing here. So then this becomes my simplified answer. Even though it may not look simple, it's simpler than what I started with. So in this case, you're just looking for, again, how many you need to pull out, and then find a device or a system that works for you to make sure you know what you're pulling out, how many, and what's left in there. I like to necessarily cross it out and then put something like this. Color coding for me works really great, but find what works for you. This will essentially work with any amount of variables and whatever root you're looking for, but the basics are still the same. So for blue, we saved the best for last. We're going to be solving quadratic equations. There's different ways in which to solve them. You can factor them, you can complete the square, you can use the quadratic formula, you can use, if you know it's a perfect square, you can use the root method. And so for this one, we're going to focus on factorization, we're going to focus on perfect squares, if we can do the root method, and then the quadratic formula. Completing the square is something that kind of goes hand in hand with other things, so it's kind of its own separate deal. I like to think of it as if you can perfect square root it, then it's the easiest. If not, try factoring it. That would be the second easiest. And then if none of those are possible, quadratic formula works for everything. We'll move completing the squares to the end of this. So here you have 9 different quadratic equations. I'm going to ask you to look for and circle, or in your head, just do this, which ones are perfect squares that you can use the root method to solve, and how do you know? So I'll give it a second, and then I'll go through. For this one, what you're looking for is, again, does it have an x term or not? Here we have x squared and 9, but no x term. Here we have x squared and negative 64, minus 64, no x term. And then again here, we don't have an x term. They might look a little bit different, but they all show you that there's no x term, so they can all be written like this first one. If I were to add 64 to both sides here, I can have x squared on one side, 64 on the other. Over here, if I subtract 3 from both sides, again, x squared on one side, I could have 16 on the other. So as long as I can write it where I have x squared alone and my number on the other side of the equal sign, these become pretty easy to solve. And what I'm looking for these is, does it have an x term or not? So they're short looking, and they're fairly easy once you get to this point. Before we solve these, again, I want you to just get used to looking at equations and knowing what can be done with them. So the next one I want you to do is look for any and all that can be factored. So in this case, you're looking for the last term here, factors of 12 that subtract to be, since there's no term here, you know it's a positive 1. Are there any factors of 12 that subtract to be, I'll use a different color here, positive 1? And the answer is yes. Both 3 and 4 multiplied to equal 12, and you can subtract them to get positive 1. So how do you get a positive 1? You need a positive 4 and a negative 3. So if you can do that, then you know this can be factored. So we know this is a factored term. Are there factors of 17 that add to be positive 10? The answer is no. 17 and 1 are the only factors. You add them together, you cannot get 10. So we can kind of narrow some of these out. Some of these are easier than others. Down here, are there factors of 3 or that subtract to be negative 8? No. 3 and 1 are the only factors. They do not become negative 8. They are not able to be done. Are there factors of 45 that add to be 14? There's a lot of factors to work with there. But I know that 9 and 5 end up adding to be positive 14. That works out, so I can factor that one. What happens if you have something like this where you have a coefficient with the x squared term? Well, you treat it the same way. Can we break this apart? We know that there are factors of 3. There's only 3 and 1, so there can only be 3x and 1x. And then are there factors of 4 that when one of them is multiplied by 3 adds to be 13? In this case, the answer is yes. 3 times 4 is 12, and 1 times x is 1. 12 and 1 make 13. Since we need both of these to be subtraction to get to negative 13, and then a negative 1 times a negative 4 is positive 4, this works. Now, by no means is this obvious. The other ones are. Some of these are. However, even if it's not something you see right off the bat, you can use the quadratic formula to solve this. And when you do, you notice you get nice, easy answers. So you don't get like radicals in your answer. You get round numbers. That tells you that it could be factored after the fact. So even working backwards, once you've used the quadratic formula and you realize that you get like super easy answers, you can always go back and then figure out, well, there must be some way to be able to factor this. If you're being asked to do so, it's not an easy or a short or fast way to do it, but it is a way to be able to tell which one can or cannot be. Best is to just look for, again, can it be solved using the perfect squares or the root method? Does it have an x term? Otherwise, look for the ones that start with just x squared, and then you don't have to worry about that first coefficient, and then look at the last term. Are there factors of that number that then add or subtract to be your middle coefficient? And then everything left over, I would use the quadratic formula for. Alright, sticking with the blue, let's actually answer one of these just for examples. For the first one, again, look for the roots. There are no x terms here, so I can go ahead and I can use a perfect square root. I can get my variable on one side, my constant on the other, and if I know that these are, again, 16 is a perfect root, then I can go ahead and square both sides. If I do that, just remember that that's a plus and a minus, and so I'm left with plus or minus square root of 16 is 4, so x can be positive 4, x can be negative 4, because negative 4 times negative 4 is positive 16, and positive times positive is positive 16. So whenever you root, just make sure you have that plus or minus, and again, that also shows up when you're using the quadratic formula. That's why you have a plus or minus before that whole thing. So no matter how this one presents itself, whether it's already in easy form or if you've got a number on the left side, just make sure you, again, separate x squared on the left, number on the right, go ahead and take the root, and that'll help you find your answer. When it comes to factoring, I picked kind of a harder one here. If you actually notice, if you can see that you can factor out of this a 2, like right at the beginning I have a 2x squared. If I can factor a 2 out of every single term, I'm going to do that because that's going to make life a little bit easier. But in here I can factor a 2 out of the first term, a 2 out of the minus 10, but I can't factor a 2 out of that minus x. So I'm not able to factor a 2 out of the whole thing at the beginning. And then I could just divide by 2 on both sides, and I really just have to worry about the x squared term. But in this case, I can't. So if I know I can factor this, then I want to look at that first term, and since it's 2x squared, I think factors are 2. Luckily for this one, there's only 2x and 1x. 2 times 1 is going to give me that 2. If it was a 4, I might be able to use a 4x and a 1x, a 2x and a 2x. It gets a little bit tougher if there's multiple terms, but for that first one, if there aren't a lot of terms, then that can also simplify things. So here I have factors of 10, that when one of them is multiplied by 2, subtract to be negative 1. Well, there's really only a couple factors of 10 we can work with. We can do 10 and 1 or 5 and 2. So even though this isn't a perfect straightforward one, there really only is a handful of options. So it can be a trial and error, or if you have the railroad method or whatever you've learned, you can try them. But for me, trial and error, there's really only 2 things you can try, and work from there. So since I know I'm not going to use 10 and 1, After looking at this, I can try 5 and 2. And so it's just a matter of, do I do 2 times 5 is 10 and then a 2 in the middle? That's not going to work out. So I need to put my 2 on the outside, my 5 in the middle. 2 times 2 is 4, and 5 can get me to -1. Since I want it to be negative, I just need the greater one on the left to be negative. So if I look this over, I kind of foil it in my head, I see that things kind of work out, and then I can go ahead and solve as though either one of these is equal to 0. So set them both equal to 0, and you'll be able to get your answers. X equals -2 is the easy one, and x equals 5 halves. The last one of the ones from the beginning that we're going to do is just a regular old quadratic formula. This is kind of ugly. We can't do what we'd like to do with it. If it doesn't necessarily come in this form, if there's, +3 or +3 on the right side of the equation, just make sure you move everything to the left side, put it in order, and get it in the x squared, x constant equals 0. And then from here we can use this in our quadratic formula. It helps to remember the quadratic formula, so if we don't remember it, x equals the opposite of b plus or minus b squared minus 4ac all over 2a. And we can go ahead and replace each of these terms with what we see from here with our coefficients. So the opposite of b, if this is b, the opposite of b is going to be +8. b squared, whether it's negative or positive, it doesn't matter, is going to be 64. 4 times a, since a is only 1, that makes it easy. 4 times 1 times c is -3. And then all over 2 times 1. So while it's a little bit ugly like this, when I simplify it, it looks like this. 8 plus or minus the square root of 64 plus 12 all over 2. Which can be even reduced further to 8 plus or minus the square root of 76 over 2. Now, some people let you leave it like this. However, if you wanted to simplify this even further, you can do prime factorization of 76, in which case you get 2 times 2 times 19. And since this is a square root, you've got 2 times 2, you can pull that out. And then that'll give us 8 plus or minus, take out that 2, you're left with 19 all over 2. You can even take this a step further. Since both of these terms can be divided by 2, we can simplify that. 8 divided by 2 is 4. 2 divided by 2 is 1. And so that ends up removing the denominator. And we get 4, and you can put a 1, but it's really not necessary. 4 plus or minus square root 19 ends up becoming our answer. As always, it's an ugly number, but with a calculator you can actually get this number, save it or store it as a variable, and then input that into your original quadratic and test it to see if it equals 0. Again, it's ugly, but calculators can handle that, and it's always good to double check your work. For equations like these, we can also use the quadratic formula. I always would, but if for some reason you were asked to complete the square, we can do that as well. So if you're given something like this, the first thing I always do is make sure that it's not a perfect square. And so I need to move this constant to the other side. I really want to have kind of a clean slate on the left to work with to complete the perfect square, and I don't want to have to worry about what I have with, the -3, and then if I'm adding or subtracting something, to make sure to do it with the 3, or to if I have factor something out, then make sure that I remembered what do I multiply that before I add it to 3. So just get rid of all that stuff and move it to the right side. If I can just isolate my square on the left, it makes life a lot easier. So I'm going to go ahead and actually add 3 to both sides and start with something a little bit easier. Now I'm still going to leave that space because I want to actually start putting stuff in there later, but right now I don't like to work with a coefficient in the first term, so I'm going to divide both sides by 2. And again, I'm going to distribute that division by 2, but I want to do that to every single term. So if I divide by 2, then that gives me something a little bit easier to work with here. I've got x squared minus 2x, and then over here I've got 3/2. And then I leave that space because I do want to make a perfect square here. So when I'm doing this, you can either foil it out and make your parentheses and really think about what that looks like, or if you know the formula, you can take your middle term, divide it by 2, and square it, and that's going to be your what you put in that space. So if we did that, my middle term is 2x, and so I'm going to take a 2. I am going to divide it in half and then square it, and that is going to give me a 1. Squared is still going to give me a 1, so I want to add a 1 right here. And it is always going to be adding, because when you square it, whether it's negative times negative or positive times positive, the answer is always going to be a positive. So I'm always going to add that at the end. Now, when I add this 1 here, I need to make sure to add a 1 over here. But I don't have to worry, because I've already factored out my 2, because I've already moved something over. I don't have to worry about it being anything other than a 1 on both sides. And that's why I moved the 3 over and left that space there, because right now I'm just working with the square on the left, and then whatever I end up doing, I'm going to do to the right. So it's key, I think, it's really crucial to set yourself up so that you're starting with just x squared plus or minus a term, and then leave yourself space. If that's what you're starting with, you don't really have to worry about much else. So I can take that middle term, I divide it in half, square it, and then add it to both sides. From there, I know this is my perfect square, so I can go ahead and just write it as such, and then just write my answer over here. I don't know if you like mixed numbers or improper, but this is the route I would go. From here, you can then square to get rid of this, but don't forget it's always a plus and a minus, and you end up with x minus 1 equals plus or minus square root 5/2. When you add 1 to both sides, there's really nothing that can be simplified, so then your answer has to be 1 plus or minus square root 5/2. There's no way to break this into square root of 5 over square root 2 to simplify the denominator, because that's as simplified as it gets. I probably wouldn't add a plus 1 at the end. It's typical to put that integer in front of the plus or minus. So that's how you can complete a square. Again, get it into a point where you have x squared and a term on the left side, whatever else on the right side, and then go ahead and perform what you know to do, however you decide to do that. But if there's an initial constant, get rid of it. If there is an initial coefficient of x squared, get rid of it by dividing both sides. You really want to start yourself off that first way. So one more example, I'll kind of fly through it and let you pause it and work through it on your own, and then you can just kind of double check step by step as you go through. So this will be the example. If I didn't know what to do, I would try factoring. I would try using quadratic formula, but if for some reason you are asked and you must complete the square, then I would immediately get rid of this plus 10 on both sides, subtract 10 from both sides, and then I'm just going to save room. If I were to subtract a 10 from both sides, then I would end up with equals negative 10. Now I have what I want on the left side, what I want on the right side. I'm just going to give myself space to be able to work, and there's no coefficient for the x squared, so I can go ahead and do that. So I'm looking for this middle term. I'm going to split it in half. So I'm going to go ahead and split that in half. I'm going to take that term and I'm going to square it. I know that equals 6 divided by 2 is 3, squared is 9. So I'm going to end up adding a 9 to both sides. I've got x squared plus 6x negative 10, and again I left that space. I'm going to end up adding a 9 to this side, a 9 to this side, and then again I have my perfect square here. So I can go ahead and write my x plus 3 squared, because I know this term's square is 3. I'm going to go ahead and simplify this side. And when I take the root, don't forget plus or minus. Sorry, do it in black. X plus 3 equals plus or minus square root of -1. I can add 3, or sorry, subtract 3 to both sides. When I do that, I end up with x equals, and again, I put it on this side of it because I don't want to add it to the right side. It just kind of looks weird. Also, if you write it sloppily, it looks like it's included under the radical, which it's not supposed to be. And then you happen to know that the square root of -1 can be simplified, so I can write that as I. It's an imaginary number, so simplified is kind of a relative term here, but my answer then becomes this. There's nothing else I can do with that. And again, I would usually write it in that order. Not that it may matter, but aesthetics. So hopefully this helps a little bit. Again, the things to remember is get your constant on the opposite side as your x squared and x term, and then do what you need to do to make sure that your x squared term has no coefficient. If that's the case, then you can kind of run through this a little bit easier and make sure just to add to both sides, and remember plus or minus with your root. But it's all in those first 2 steps and making sure it's set up correctly. If you've got that, you should be pretty good. The last beast you might see in the quadratics is enough to make some high schoolers even cry. In fact, all my middle schoolers for sure. Something like this is terrifying. But if you know substitution, you can still tackle this. Not saying it's easy, but it's easier. And so if you know that you can substitute this whole quantity for, say, a, and if you look at your powers and you know one is squared of the other one, then that helps. So I can say a is x plus 1 quantity to the 5th power, and if I do that, then this first term becomes x plus 1 to the 1/5 power squared, 2/5, because 1/5 times, or 1/5 plus 1/5 is 2/5. So when I square, I end up getting another power. Minus that 2 stays the same because it's just a coefficient of these, and I end up with x plus 1 to the 1/5 is a, minus 8, not affected by my x, my 1, my 1/5, whatever, equals 0. And I look at it like an x squared minus 2x minus 8. You can think of it as x squared plus 2x, a squared minus 2a minus 8. But here, this is much easier to simplify. And so if I were to rewrite this and kind of give myself some space, we'll go ahead and solve it. So I would choose to factor this, and when you do, let's see, I got my a's. I know that factors of 8 that subtract to be 2 are 4 and 2. 4 and 2. So I make sure I subtract to be a -2 there. And then go ahead and solve for a. I know that a equals 4 and a equals -2 because one of those two or both of those two have to equal 0. So when I solve a minus 4 equals 0, a has to be 4. A plus 2 equals 0, a has to be -2. But I also know that that a is not really an a. At the beginning I substituted, so I can go ahead and substitute back in for a and replace it with that x plus 1 to the 1/5 power, and then do the same thing over here. And how do I get rid of that on both sides? Well, how do I get rid of something squared? I do square root. So how do I get rid of something to the 1/5 power? I multiply it to the 5th power, or 5 over 1. So I can go ahead and multiply this whole thing to the fifth power, which means I then have to multiply, do the root 5, not root 5, sorry, square, not square, sorry, multiply by the power of 5. I'll do that to both sides here, to the fifth power, and then that leaves me with just an x plus 1 is equal to 1024, and over here an x plus 1 is equal to negative 32, and then I go ahead and subtract 1 from both of these, and that's going to give you your answers. X equals 1023, and looks like negative 33. So again, this thing was ugly at the beginning. If you replace it, it becomes something pretty simple, and then when you're finished, just make sure to replace it back. And if you have something to the 1/5 power, if you want to get rid of it, multiply by the 5th power. It's kind of like the reciprocal. It's going to undo that. So if you got 1/5 times 1/5 was 5/5, gets rid of that. Just make sure you do it to both sides of the equation, to both answers that you get, and make sure to finish it out. So the best thing about this is you're probably not going to see too many of these, so just practice them. As long as you can do 1 or 2 basic, simple, I wouldn't spend too much time on it. But congratulations, this whole test looks like a monster. But if you can break this down by section by section, and then even with all these quadratics, know what to look for and know what to do in each situation. It's systematic, so step by step. Study hard, you'll be good. I feel like that's a pretty good summary of quadratics. But for the whole test, just remember basic things to take away from in the beginning. If you have polynomials and you're adding, subtracting, multiplying, dividing, if you have addition or subtraction, just make sure that you get common denominators. And if you have subtraction, don't forget then, if you've got a term, and it doesn't matter, but if you've got a subtraction, that you distribute that to all parts of the second term, especially the second numerator there. And when it comes to multiplication and division, if you've got division, multiply by the reciprocal. When you've got multiplication, go ahead and cross-simplify like crazy. Do not do that when you're adding, subtracting, but over here, do it till your heart's content. When it comes to cubes and sums and differences, just make sure you remember the pattern. Again, if you start with a plus, then it's going to be plus, and then minus plus. If you start with a minus, it's going to be minus, plus plus, and again, whatever these terms are, square this one for here, square this one for here, multiply them together for the middle. So it's pretty formulaic, but if you have that on the test, that formula, that should be helpful. When it comes to long division, just remember you're looking at this first term and your biggest term, and you're figuring out what do you need to multiply to get there. So since it's positive, positive, I need to multiply by a positive x to the third. So I'm going to line that up over my x to the third, and then again, just kind of distribute, multiply x to the third times x is x to the fourth, x to the third times 4x's. And so I'm going to go ahead and then when I subtract, I want to make sure I remember I'm subtracting the whole quantity. So this becomes minus, this becomes minus as well, and I can continue working. So you're always trying to match your first term here with your biggest term available, and once you cross these out, your next biggest term available is x to the third, and so you're constantly just trying to make sure what's the multiplier that's going to help me get that. When it comes to roots, you want to make sure you know if you're looking for this, the square root, the cube root, the fourth root, the fifth root, whatever, and then prime factor whatever is inside. So if I have 27 a to the fifth, and I know I'm going to the third root, then just break this down to all of its prime factors. And then again, if I'm looking for 3 of something, cross out 3, I get that. Cross out 3, I get that, and I'm left with what's left. And so again, know how many you're looking for, and then know again what your primes are and whatever's left over. So I can pull out a 3, I can pull out an A. Remember that that's cube root. Whatever's left over, I'm just going to leave inside. Again, squished back together, I hate to say it that way, but simplified, multiplied together in its simplest form. When completing a square, even though we talked about quadratics already, it's kind of its own thing. Just make sure again that you have your constant on one side and you don't have a coefficient with your x squared. After that, you can go ahead and follow the formula. Find your that middle term of your square, half it, square it, add it to both sides of the equation, and then go ahead and then make sure that you, when you take the root, that you include the plus or minus. And then for whatever's needed on the test, don't forget your I table. I is the simplified version of square root of -1, so that is your imaginary numbers. No matter what you have as a negative in the root, you can always take out the I as a -1 and then leave whatever else is there in the root. I squared is negative, square root of -1 times square root of -1. Whenever you have a square root times a square root, they cancel each other off. I to the third is just like I times I squared, so -1 times square root of -1. And I to the fourth is I squared times I squared, so -1 times -1, negative times negative is positive, and then you know the fifth root is the same as the first, the sixth root is the same as the second, so that's that table that continues to cycle through. I think that's everything. Again, take this and break it up by color, break it up by section, break it up however you want. I know this is super long and I apologize, but hopefully you'll be able to kind of, again, pause and do what you need to do and not have to watch a monster of a video over and over and over again, but whatever you need. So use this as, you know, like a chapter book and just flip to the chapter that you care about at the moment. Good luck. If you need anything else, just give me an email and, you know, do well.